Okay, so we are officially caught up to, we've looked at everything in week 1. I didn't see any issues with week 2. If you're behind, it's okay. Like I said previously, I'm only going to do about 5 grading sessions for this course. I'm going to do one in week 3, which is at the end of this week, so get your week 3 things done. I'll just do some grading on Sunday. So by, come Monday, you'll know, hey, I'm caught up or not with the first 3 weeks of class. What's that? Well, if you're not, it's okay. No need to confess. It's not church. But just get caught up with the first 3 weeks by Sunday evening. That's when I'm going to do my grading. Mondays I usually do a lot of professional development stuff on Monday, but then I'll see you a week from today, and hopefully you'll know where you stand in the class in terms of what you got, what you didn't get. We can do a little bit of Q&A on some of the trickier things, but I'd like by week 3 to have everybody caught up on all the exams and assignments. So
This is the class I'm worried about.
we'll get you there. It's okay. All right, so here we are in the Moodle shell, site surveys and pre-planning. The exam is right there at the top. Here's your assignment. Not sure how that could be any simpler. Read Chapter 3 in photovoltaic systems. Pretty easy. Week 3, Chapter 3. 2-hour time limit. Plan ahead. Okay. There's a deal on magnetic declination. I love this topic. I was fortunate enough last week to be traveling with another scientist on main campus in the geosciences by the name of Jim Sears. And this guy will go kayaking in Siberia, around Montana, looking for ancient rocks that have their magnetic poles pointed south, because the Earth's magnetic field flip-flops every 600,000 years or so. And it wanders around. Like the Earth's magnetic field is a function of a bunch of very hot metal spinning at the center of the Earth. We don't cover it. Well, we cover it a little bit in this class, but in fact, I don't even mind.
Geothermal covers it pretty
well. Yeah, Jonathan Bowe covers it pretty well, but I like going back. Always love going back to the dynamic periodic table.
I just read something here. I don't remember what it was for even. It might have been one of my classes, but we're actually upside down on it.
Oh, really?
North is actually south, apparently.
Yeah, well.
According to a magnetic.
Well, yeah, and I guess that's the thing about the magnetic field, is that calling it north or south is just a human convention, right? And the electromagnetism has to do with how, more or less how electrons behave. And if you go right back here to the periodic table, and I love to just click on iron. If you look, and I don't know really as much as I should about what makes, iron a material that can become what's called a ferromagnet, a permanent magnet. But if you do look right there in the 3D orbital, if you guys can see that kind of right in the middle, the 3D orbital, and if we look at that guy, it's a little weirder looking. The 1s orbital. No, it's not showing up right now. I can show you. Should be able to see the 1s. The 1s orbital is kind of simple, boring, plain, a sphere. The 2p orbital. Let's go out here to iron again. Actually, let's go to something a little simpler. The p orbitals are just 3 little dumbbells. Dink, sort of x, y, and z. Once you start getting up into the heavier elements, the orbitals look different, sort of like, I'm not sure what you'd call that thing, like, kind of 4 biscuits maybe. There's another 4 that are perpendicular to the first 4. That's a toroidal shape. So the blue thing is a torus. It's a donut. The other two are kind of dumbbells. Keep moving out. We've got another set of, pan of biscuits, and then yet another one. And it could be, and again, if I were, better physicist, I would say, well, the fact that this thing has electron orbitals that look like magnetic fields, because the magnetic field itself is toroidal. Just if we'll take a look at that in a second, how the magnetic field lines point out of the North Pole, go back to the South Pole. These little spins that each one of the electrons have, and they're either spin up or spin down, basically act like little tops. And a top is either spinning on its head or on its tail, and that's where the whole north-south thing comes from. You add up all of these spins in the Earth's core, and then you get your magnetic field. Like we said before, it flip-flops every 600,000 years, and it's moving all the time. It's not always pointing in the same direction. So let's just bop out for a second.
60 miles a year, 32 miles
Yeah,
a year.
yeah. And it's not linear either, but you could sort of say average, maybe it's 60 miles a year, 30 miles a year.
Well, at the top or something, I don't know.
Yeah, no, that's a reasonable average. Let's just look at images here.
I remember better, but wintertime I went into full vegetation mode.
Okay. So if you happen to live in Minnesota or here in Iowa, some of the other Midwestern states, you don't have to worry about magnetic declination. Your compass is going to point in the same direction that, more or less the North Star is pointing. And just to make some hand gestures here. So actually, let's go back out. Yeah. So here's another little image. You can sort of think of the axis about which the Earth is spinning as its mechanical axis, and then the magnetic north, if you will, as the magnetic axis. And they're roughly the same based on the physics of how the shear stresses within the Earth's crust drives the mantle, et cetera, et cetera. But like we said, it flip-flops every now and then. This is the north that we're concerned most about, because it's the mechanical direction that the Earth is pointing that tells us what direction south is. Because in general, and we covered this last time, you want your system to get as many photons as it can. You do not want your PV system to be pointing north. You want it to be pointing south. And not only that, you would like it to be pointing at a proper angle. So you've got the azimuth angle, which is the east-west, and you also have the elevation angle, which is sort of the up-down. So what we're doing, as the Earth is spinning around the sun, we're trying to keep our PV panel pointed at the sun. You might be able, so it's pretty easy to walk outside with a compass. Here we are in Montana, and we're looking at almost 14 degrees. So it's just basically a matter of looking at where your compass is pointing, subtracting 14 degrees, and that's how you're going to set up your system. So, okay.
Now, as seasons go,
You could also, you could bias your compass so that it's pointing north. Yeah, absolutely. Yeah. Question?
Do you change the angle of the PV panels with the seasons? If it's not tracking, or do you just set it and forget it type of deal?
So you mean you change the elevation angle with the seasons?
Yeah.
There are systems like that, and
let's say you can't afford that kind of a system. Would you go up there and manually do it?
Yeah. What we'll see, and we'll get into the trigonometry here a little later, but what we'll see is that what you're dealing with is the sine of an angle that is very close to 90 degrees, or the cosine of an angle that's very close to 0. In both cases, what we'll find is just by even moving 5 degrees, you're talking maybe a 1 or 2% gain.
Oh, so
And, yeah, and, right. And so it's like, is it really worth my time to climb up on the roof and move the thing, or to, add another level of complexity by some kind of motor or thermal fluid pump, which is the kind we have at our one that used to be out in Hellgate Canyon. It's another thing to break, it's another thing to touch. So in general, you sort of weigh that complexity cost over setting it up, optimally the first time. And usually,
36.1.
yeah, and usually it pencils out just to set it up right the first time and optimize that way. Okay. Let's just take a quick look at this guy. Geographic or true north. I was calling it mechanical north, but geographic, true north, celestial north. Yeah, so this is what we just covered. And 14 is about where we are. Just showing those differences. You can either, add 14 to 0 or add it to 180. This is just showing further declinations. Let me just take a look at these guys too. All right, so this is a lot, and we'll get into this when we do some site surveys. We'll get the Solar Pathfinder out. In fact, let me show you. I'll show you one of my own Solar Pathfinder results that I did. It's kind of fun. I think I've got it in my professional engineering jar over here. Did it at the Hive, geothermal, solar PV, trom wall, awning east. Okay, so what we're looking at right here is, well, I'll show you what the Solar Pathfinder is. There's one in Naomi's office. If you ever need to check it out, like literally you can. The Pathfinder itself, yeah, here's a good shot of it. It's just a little dome, a little globe, and you'll set it up. It's got a compass built in, so you'll set it up pointing north. You'll put in this little sheet of paper, and the sheet of paper is going to be rated for a given latitude. Like you're going to use a different one if you're at the equator, another one if you're way up north here. But what you end up with is a shadow of all of the surrounding trees, buildings, power lines, what have you. And if you look closely, it's not that easy to see. If you look closely, each one of these numbers is more or less an hour, like an hour or two. This is like an hour of sunlight that you will get. So this is 11 a.m., 10 a.m., 9 a.m., 8, et cetera, 12, 1, 2, 3, 4, off into the sunset, more or less. If we look closely, we can see that's December, that's January, that's November, this is February, this is October, March, September, April, August, May, June, July. So the March and September solstices are right there in the middle together because the sunlight is about equal. The if you notice the oh, did I say solstice? I meant equinox. Yeah, sorry. The spring and autumn equinoxes are right there together because they're equal. Thus the name equinox. Thank you. Yeah.
June, December.
No. Yeah. So there we are. So June is the summer solstice, and what you see here, you see this nice long line, right? Sort of starting 6 a.m. going all the way out, past 8 p.m. So you've got sort of a longer line there. If you get up into December at the winter solstice, the days are just shorter. Here comes the sun at 8 a.m. and then it sets, 4:30 or whatever. So from there, it's just a matter of counting up each one of those little hours. You just add them together. And I made a sweet little spreadsheet, I think. I don't know why my computer wants to do this to me. Yeah, this is one of my finer efforts. I'll just tell you, I'm quite proud of what I did here. I took the shading data that I just showed you from the Solar Pathfinder and just stuck it right into a spreadsheet. And you can tell what I did was make the Excel spreadsheet look a lot like that crescent shape from the Solar Pathfinder. So what I did was just gray out the shadows. So each one of those little squares in the Solar Pathfinder became an entry in the Excel spreadsheet. Then I just let Excel add all those numbers up for me. From there, I turned that into energy in megajoules or kilowatt hours. I then took that energy and turned it into just BTUs. I mean, at that point, you can change it at any type of energy. And so the point was to say, hey, if you build this passive solar array using the data we got from the Solar Pathfinder, it's going to save you this much energy because you're not going to have to burn that natural gas. That was it. So that's how the Solar Pathfinder can actually give the site planner a solid estimate of how much energy they're going to get. You mentioned before deciduous trees. Well, you want to be careful, like, hey, am I seeing that? I don't know if any of these guys, yeah, oh, right here, perfect. You're like, okay, so this was summer, and all you're going to do is take your pencil, mark that off. Those are the hours you're not going to get. Everything to the right of that, everything in the middle, you are. So it could be like, oh, well, shoot, if I just move it back a little bit, maybe I do some tree trimming, you know, at that point you're really optimizing how much sun you're going to get.
So in the middle of a football field, you're pretty much not going to have any shadows on that then.
Pretty much, yeah. So middle of the football field, if you're in the stadium.
Right. Yeah.
So
So
the elevation does matter.
Right.
And we did this a little bit. Yeah, and that can sometimes be tricky, especially if you're going to do a pole mount. You're actually going to want to stick that. If you're doing a pole mount, and there are plenty of pole mounts. You don't want your Pathfinder down here at the ground. You want to stick it up as high as the array will be, so that you get an actual. The higher you get, typically the more sun you're going to get because there's less infrastructure blocking it. Yeah.
So if you're going to put that on a roof of a house, you'd have to make a little platform for it to sit on so it's level.
Oh, it's got a little tripod, and each one of these will extend, so it'll level itself. In fact, that little bubble right there is the 2-axis leveler, just like a laser sight or survey. You'd go on the roof. Oh yeah, you'd hop right up on the roof, and if you couldn't get level enough with the Pathfinder, yeah, you could build a little triangular platform and stick it there.
These
So.
are roof houses, so I know how things are.
Yep.
So young and dumb.
Yep. Well. Okay, so that's the Pathfinder. Here's another shot of it. Again, you want to make sure that you've got the right latitude, 43 to 49, and we're at 47. We've run these in the past. Yeah, and then your next step in your PV layout is where are the panels going to go, and that's where you get a little bit creative, because you want to make sure that. Again, you're not putting the things in the shade. You also want to make sure that you're not making your wires too long. In fact, just today, in NRGY 299, we're planning out the wiring diagram for our electric car. And obviously, the longer you make the wire, the more energy you lose in power. So at this point, what you're trying to do is play those two variables against each other. Like, oh gosh, if I stick this panel way up on the northeast corner of my roof, I'm going to catch the most sun, but it could be that you're now getting burned by extra expenses in wire and line losses. So we can get into the details, but that's kind of your next little step when you identify, here's where the most sun is, but is that going to allow my system to perform well also? And there are sort of three separate circuits. I think what this particular setting is where the panels are going to be wired in series rather than parallel, perhaps with three separate inverters. That's another thing to consider. We'll get into what, micro inverter versus large inverter, series versus parallel, and what that means. But that's what those three separate colors mean in this particular.
So when you're setting
setup.
up your panels, does it do any good to face some more eastward so you catch the morning sun better?
Yeah,
Go
good,
down like that?
good question. So the question is, would you want to sort of cheat the panels eastward or westward? Well, if you knew they were going to be in the shade in the afternoon based on your solar Pathfinder, yeah, wouldn't be a bad idea to have them pointing in the direction where they're going to receive the most sun.
But all the panels at the same,
Yeah.
so you wouldn't have some set this way and some set like that?
Yeah,
Or is that another one of them things where it's probably not efficient enough?
well, that's a great question, and let me show you. It's a great question, because a little bit of creativity comes into it, for sure.
Greg was saying something about if they're in series, then, and you've got some facing one direction, some facing the other, the only greatest power that you're going to generate is
Yep. Yep.
that one direction.
Yeah, I was just thinking, like, if you designed your own panels and you made like a dodecagon or something, where it arced around.
Oh, yeah.
Or something, or set up your panels that way. I don't,
No, I'll tell you. This house. Let's just look at this house. This is a house that I did a little professional engineering assessment for. And let's see, this guy. Let me think here. This is the east side of the house. This is the north side. Where you see these trees in the back, that's the south side. There's a panel sitting right here on this gable. There's another panel.
Yeah. You wonder what I was it's just sharp.
Yeah, it's cool. No, it's great. So there's one panel sitting on the eastern roof, and there's one sitting on the western. And what you just brought up there, Todd, is a great question. So if those two panels, or there are two set, I think there might be two or three, and you can walk or drive right by this thing. It's just on Mount Street. So both of these had to be racked so that they're not only on the roof slope, but the rack is built in such a way that two sides are longer, two sides are shorter, and it's pointing south. Now, what you brought up is valid. You wouldn't want a panel here and a panel on the western side that weren't pointing the same direction. In this case, they are. But if for whatever reason, said, hey, I'm just going to flush mount that. One's going to get morning sun. Flush mount the other one. It's going to get evening sun. Solar panels themselves are resistive devices, and if they're wired in series and one's at a higher voltage, it's going to try to push its electrons through the whole system because it's in series, and the ones that are not pumping electrons are just going to suck that energy in, and you're going to lose a lot of efficiency. So yeah, you want them all. Anything that's wired in series, you want to be receiving the same amount of sunshine all the time. Yeah. Yeah.
Otherwise, you have to set up separate battery banks, separate panels.
Well, yeah, or you'd need a combiner box but they'd be separate circuits. You'd want to wire them in parallel. Yeah. You wouldn't necessarily need battery banks, but it just adds complexity, yeah. Okay.
I just know how good the morning sun feels.
Yeah.
It's just coming up.
Yeah, the morning sun deal is more a deal for passive solar, for solar thermal, where you want to get that energy in right away when you've had a cold evening. Okay. Let's see what else we got here. All right, so we've seen the Solar Pathfinder. There was a little Google Sketchup. If you guys want to use Google Sketchup, you can kind of teach it to yourself. It's more or less draw a box, drag it, color it, done. And then you can then take that and put it somewhere on Google Earth as well. I taught it to myself a few years ago. My son taught it to himself. We're not going to spend time teaching Google SketchUp, but just
I used it to design snowmobile handlebar risers.
mm-hmm. Yeah. Here's something notable, and I'm not going to look at it now because it's kind of time to wrap up. But a few years ago, I put some solar PV panels actually on a, and I'll dig up the video and post it online. Put the PV panels on a shipping pallet that we bought some PV panels on, put it behind my bicycle and kind of dragged it downtown, showed that at Caras Park. There was just one little shade, like one tiny little bit of shade from one of the wheels covering one of the 54, or however many it was, cells. And that too affects the performance because on the panels, every one of those cells is wired in series. So it's just like, if you've got it shaded, it's like snipping a chunk of wire out of your series circuit. Okay. I'll let you go through PV watts a little bit. We're just going to go back to version 1. What PV watts is going to help you do is start with some of those calculations we did with 1,000 watts per square meter. It's going to say, hey, I'm at 47 degrees north. PV watts knows how many hours of sunlight you're going to get. Very similar to what we just saw with that Pathfinder, and it'll take you through that. So I will let you dig into the PV watts on your own. And if there's any questions, here's where to post them. So I'll be ready and waiting. All right, guys. Week 3 is behind us. Well, we're in the middle of it. Thanks for coming. $28 minutes.